Hey math friends, this is AP Calculus section 7.2 notes. We are going to be continuing to talk about applications of integration today, and we started by talking about modeling with differential equations in section 7.1, and in section 7.2 we are going to be talking about slope direction fields. Now we have looked at slope direction fields a little bit already this school year, so now we're revisiting this topic again. But the idea here is that suppose we have a differential equation and we have at least an initial value of a function. We should be able to sketch a picture of what the curve might look like that would be a solution to that differential equation. Because if we have the differential equation, basically we have an equation to calculate slope at any point on the curve, right? So our steps here are just going to be to build a table to find the slopes at different given points on our curve, and then sketch our slope field, and then use the initial condition and the slope field to sketch the solution curve. And I think this will make a lot more sense here as we work through our examples today. So in example 1, we're given the differential equation y prime is equal to x squared. And obviously we have an equation for y prime, which we know the derivative is slope, right? And we are asked to sketch a potential equation for y. And in fact, A, B, and C were actually asked to sketch 3 different potential equations given different initial conditions. But before we can even do that, first we need to sketch our slope field so that we know basically the path that our curves will follow. So the first thing that I want to point out about our first example here is that y prime is equal to x squared, right? So our slopes are going to depend only on the x values of our ordered pairs. So right here, I'm just going to kind of point that out. Our slopes will only depend on x values of our ordered pairs. And this is because y prime is equal to x squared. We don't have any y's on the right-hand side of the equal sign. We only have that x squared. So our slopes are only going to depend on the x values of our ordered pairs, which is going to make building my table much easier for my slope field. So I'm literally just going to build like a t-table here. And over here, I'm going to put ordered pairs, and then next to it, I'm going to put the slopes at those points, right? Because I know my equation for y prime, which gives me slope, is equal to x squared. So since our slopes only depend on the x values of our ordered pairs, let's say x is 3, right? It doesn't matter what y is. The point could be 3, 3, it could be 3, 2, it could be 3, 1, 3, 0, 3, -1, 3, -2, 3, -3. It doesn't matter. All of those points are going to have the same slope. And the slope is going to be what I get when I plug 3 in my y prime equation, which 3 squared is 9. Okay, so whenever x is 3, my slope is 9. Well, if we look at our graph here, x equals 3 is a vertical line, right? So the idea here is I'm going to try to graph a slope of 9 in a vertical line along the line x equals 3. Obviously, a slope of 9 is a very steep slope, right? So I'm just going to kind of do my best to graph what I think a slope of 9 might look like. Then the next x value that I could have would be x equals 2. And again, every ordered pair with x equals 2 is going to have the same slope, and that slope would be equal to 2 squared, which is 4. So along the vertical line x equals 2, I'm going to try to graph a slope of 4. So obviously not as steep as 9. When x is 1, my slopes will be 1 squared, which is 1. So I want to graph a slope of 1 when x is 1. When x is 0, my slope is going to be 0, right? So those are going to be horizontal segments here for my slope. When x is -1, I'm going to start repeating now because -1 squared is +1. So all my slopes are going to be +1 again here when x is -1. And when x is -2, my slopes are going to be 4. I maybe put a little too much slope on that. Trying to make a slope of 4 look different than a slope of 9 is a little bit difficult. And then finally, when x is -3, I know my slopes are going to be 9 again. So it's kind of as steep as I can get without looking vertical for the most part. Okay, so I've sketched my slope field. So now I can actually use my initial values to sketch the different possible solution curves. So at this point, you're probably going to want to grab 3 different colors, either pens or colored pencils or markers or highlighters, something like that, because we want to be able to differentiate these 3 functions. So my first one, letter A, has the initial condition y of 0 equals 1. Okay, so I am going to sketch the solution curve for that in blue. So that means that y of 0 equals 1, that's an ordered pair on my curve. That means when x is 0, y is 1. So my solution curve for letter A has to pass through that point. And then basically I am just sketching, and I kind of did a poor job over here. There we go. I'm just sketching what my solution curve would look like by following the slope field. Okay. My second one, I will graph in pink. And my initial condition is y of 0 equals 2. Okay. So again, there's the solution curve for that one. And then my third initial condition would be y of 0 equals -1. So that's going to start there and look like that. Okay. So notice that all 3 of the functions that I graphed have the same basic shape. This basic shape is the shape of a snake or a cubic function, right? And it does make sense that no matter what the initial condition is, we should end up with a family of cubic functions because our differential equation was quadratic, right? And what would the integral be of a quadratic function? It would be a cubic function. So it makes sense that if the derivative was quadratic, its solution or its integral would be cubic. This time we are given the differential equation y prime is equal to y plus 2, and we're doing the exact same work that we did in the previous problem. Now for this one, this time note that our slopes are going to depend only on the y values of our ordered pair. And this is because on the right side of our slope equation or our differential, we just have y plus 2. X does not appear on the right-hand side of the equal sign. Therefore, our slopes are not affected by the value of x in the ordered pair. They are only affected by the value of y. In examples after example 2, we will have differentials where our slope depends on both x and y, and then you'll see how that makes graphing a slope field a little bit more complicated. So for this one, I'm going to do what I did in the previous problem. Right, I'm going to create this table here, and I know that my slope, my y prime, is going to be equal to my y value plus 2. And over here, I'm just going to start putting ordered pairs. Now, since my slopes only depend on the y values, I don't really care what x is, right? I'm going to build my table based on my y values. So something comma 3, something comma 2, something comma 1, something comma 0, -1, -2, and -3. Okay, so when I start plugging these in to get my slopes, when y is 3, 3 plus 2 gives me a slope of 5. When y is 2, 2 plus 2 gives me a slope of 4. When y is 1, 1 plus 3 is 2. When y is 0, 0 plus 2 is 2. When y is -1, -1 plus 2 is 1. -2 plus 2 is 0, and -3 plus 2 is -1. Okay, so now notice that my slopes are going to be in horizontal lines this time. because my slope only depends on y, whereas in example 1, my slopes were in vertical lines. So anywhere that y is 3, so basically the horizontal line that runs across the top of my graph, my slope is going to be 5. So I'm going to kind of try to sketch something that's pretty steep here. This is a slope of what I'm calling 5 on this graph. Then when y is 2, so the horizontal line right below that, my slope is slightly less. It is a slope of 4. So again, we're just doing our best to try to make our slopes look a little less each time. When y is 1, my slope is 3. When y is 0, my slope is 2. And when y is -1, my slope is 1. When y is -1, or sorry, when y is -2, my slope is 0. When y is -3, my slope is -1. Sorry, got a little crazy there at the end. I can do better. There we go. Okay. And now I'm ready to sketch my solution curves for each of my 3 different initial values. So again, I'm going to do these in different colors just to differentiate them. My first initial value is y of -2 equals 1, which means the ordered pair, -2, 1, which is right here, right? So I'm sketching the curve that passes through that point and follows my slope field. So it's going to look something like that. My second one I will do in pink. And my initial value here is y of 3 equals 2. So that's just the ordered pair 3, 2. Okay, that's right there. And again, sketching that. Oops. There we go. And then my third one I will do in orange. Y of 2 equals -3. So the point 2, -3. So now we're below that. And so this is going to look like that. Okay. And then there's a question below for us to answer here. It says, what happens to every solution curve as our x values approach -infinity, and why, right? Well, if you look at our 3 graphs, we have that horizontal line at y equals -2 where our slope is 0, right? So each of our solution curves basically become, kind of approach a horizontal line at that point. So the answer to this question below here is that as x approaches -infinity, all of the solution curves approach y equals -2. Okay, and why is this? This is because y equals -2 is a, oops, I can't write. Y equals -2 is a horizontal asymptote on the graph. I'm not sure why it's being difficult for me right now. Let me try again here. Y equals -2 is a horizontal asymptote on the graph. Okay. We are on to our third example here, and this time the differential equation that we are working with does not depend on just x or y. As you can see here, this one, the slopes depend on both x and y values. Which is going to make our table and our slope field a little bit more complicated. So when we have a situation where calculating our slope involves us plugging in both the x and the y value of the ordered pair, we want to be looking for patterns. And I will explain what I mean to kind of streamline the process as best that we can, shortcut things a little bit. Okay, so I'm going to make my table here. X, y ordered pair on the left, and my slopes are my y prime is equal to the opposite of x divided by y. All right, so when I start thinking about ordered pairs, obviously the first one that I'm going to think about is going to be 0, 0. And the problem is 0 divided by 0, I know that that is undefined. Okay, now let's have this conversation right here, right now. If you have undefined slopes in a slope field, you do not put any line segments. Okay, you don't put vertical line segments for an undefined slope. You leave it empty. You leave it blank. If they ask you to sketch a slope field on an AP exam, they're going to be looking specifically for that. If you have undefined slopes, they're going to be looking to make sure that you did not put any lines in there. All right, so then the next thing I would notice is, let's take a look at the point 1, 1, which is, interesting because x and y are both the same value, right? Well, if I take 1 divided by 1, that gives me, or 1 divided by, 1, that gives me 1, and then the opposite of that would be -1, right? Well, what if my ordered pair is 2, 2, or 3, 3, or 4, 4? The same thing is going to happen. I'm going to end up with a slope of -1, right? So if I've got x, when x is equal to y, so like if x is 1, 1, or if x is -2, -2, it doesn't matter. Basically, the idea here is when x equals y, my slope is going to equal -1. Okay, so I'm going to go ahead and I am going to sketch those in right now. So when x equals y, those are kind of diagonal lines through my graph, right? When x equals y, so like 1, 1, 2, 2, 3, 3, my slope is -1. So I get something that looks like that. And then -1, -1, -2, -2, -3, -3, same thing, okay? Well, now you might be a little bit curious, what if x is the opposite of y, right? Well, what does that make? Well, let's take a look. What if I've got -1, 1, or I've got 2, -2? So basically what happens when x is the opposite of y? Well, my slope ends up being +1 in that case. So I go back to my slope field and I'm going to sketch those slopes in. That's going to be this diagonal line right here through my slope field. Okay, so this is looking kind of interesting so far. And then the next thing that I might explore is, well, since what I have in the numerator is an x, right? Anytime I put 0 in my numerator, doesn't matter what I put in my denominator, except for 0, obviously. We already addressed the 0, 0 ordered pair. That one's undefined. But 0 divided by any number, when x is 0, my slope is 0. Okay. So I can go ahead and I can sketch that in. When x is 0, my slope is 0. So I'm going to have horizontal line segments all along my y-axis except at 0, 0. All right, well, what about when y is 0? Okay, let's look at that pattern next. So if I've got an ordered pair, some number, comma 0, I know that all of those slopes are going to be undefined. And again, that means no lines on my graph, because when y equals 0, we're dividing by 0, and our slope is going to be undefined. So we are not going to have any sort of slope segments along our x-axis when our y values are 0. Okay, so that's kind of the best we can do as far as trying to look for patterns in our slopes. And now it comes down to a little bit more tedious of work. We just have to start plugging in ordered pairs and kind of try to see what's happening here. So for example, what if I plug in the ordered pair x is 2, y is 1? I would end up with negative 2 over 1, which is going to be a slope kind of like that. What about if x is 3, y is 1? Well, then I end up with negative 3 over 1, so a little bit more steep. Okay. What about when x is 1, y is 2? I end up with negative 1/2. What about when x is 1, y is 3? Negative 1/3. Okay. So I don't know if you're seeing it yet, but, and these are all going to be opposites over here, but we're kind of getting this sort of semicircular shape going on here, right? We've got these slopes, and I know what this looks like, so I'm kind of taking the liberty of sketching these in here. But we've kind of got these slope fields. Whoops, that one was not correct, sorry. Kind of got these slope fields here that are looking sort of like circles in our coordinate plane. There we go. Okay. And so now we can go ahead and we can sketch what our solution curves are going to look like. I'm going to use blue pen for my first one. And my first solution curve, it contains the point when x is 2, y is 1. So right there. Okay, and again, I'm just going to follow the slope. But the x-axis is undefined. So when I get to that point, I stop and I draw an open circle. And then I continue following my slope field here. And again, then I have to stop when I get to that x-axis and I have to draw an open circle. I apologize, that looks a little lopsided there. Okay, let's take a look at the second one. I'm going to do that one in red. When x is negative 1, y is negative 2. That's that point right there. And I'm going to do the exact same thing. Okay, I'm going to try to follow the curve here. And again, when I hit that axis, I have to draw an open circle because I can't intersect that line. It's undefined. And then my third one, well, this one is going to be a little easier. When x is 0, y is 3, oh, well, I know exactly what that's going to look like. That's going to intersect right here at 3 and right here at 3. That is going to be a perfect semicircle here with a radius of 3. There we go, okay? So a little note here, what happens to our solution curves as our y values approach 0, and why is that? Well, the answer to that question is all of our curves stop, and by stop, I mean we show that with open circles on our graph when they reach the x-axis. Okay, because we have undefined slopes when y equals 0. Okay, there we go. Okay, so that's the reason behind that. And you might want to put a little note here that all of our solutions are either the top or the bottom half of a semicircle, depending on where that initial value for our curve lives. Does it live in the top half or does it live in the bottom half? Example 4 is our last example, and this is similar to example 3 in that our slopes, again, are going to depend on x and y values, which is going to make our table a little bit more challenging. But we're going to do the same thing that we did in the previous problem. Oops. We're going to look at our xy ordered pairs, and we're going to try to look for patterns to make our life a little bit easier. And here we know that our y prime, or our dy dx, is going to be double the y value divided by the x value. That's going to be our slopes. All right, so I always like to start with 0 here. So if x is 0, and remember x is in the denominator of our slope, if x is 0, it doesn't matter what the value is for y, right? This is going to make undefined slope for us. And again, no marks, right? No lines for those undefined slopes. So let's put a little note. When x equals 0, slope is undefined. Next thing that I might consider is that my slope is always going to be twice my y value over my x value. So I'd like to think about, well, what happens when my x value equals my y value? Since x and y are both positive in this situation in my slope, when x equals y, like for example 1, 1 or -2, -2, it doesn't really matter. I'm always going to end up with a slope of +2. Okay, so let's go ahead and sketch those in there. When x equals y, my slope is going to be +2. Okay, so I have something that looks like that. And then the next question that I would probably ask myself would be, well, what if x is the opposite of y? What does that look like? So for example, -1, 1 or 2, -2. And the answer is those are going to give me a slope of -2. So I can go ahead and I can sketch those in. So this is kind of strange looking so far. It sort of looks like a weird X kind of shape. What about, I already looked at when X is 0. So next, let's maybe look at what happens when Y is 0, because Y is in my numerator. And obviously the exception being when X is 0, but whenever Y is 0, doesn't matter what X is, my slope is always going to be 0. Okay, so I can go ahead and I can sketch those in. That's going to be my x-axis, the exception there being the origin. So I have horizontal slopes here. Okay, and that's kind of the best that I can do as far as looking for patterns are concerned. So now I just need to start grabbing some random points and plugging them in and knowing that the point across from it is going to have the opposite slope. So for example, when x is 1 and y is 2, I end up with 2 times 2 is 4 divided by 1 is 4. So right here I'm going to have a slope of 4, and across from it I'm going to have a slope of -4. When x is 1, y is 3, that's going to be 6 over 1. So again, I just keep getting steeper here. When x is 2, y is 1, I end up with 2 times 1 divided by 2. So that's just going to be 2. When x is 3, y is 1, I get 6, or sorry, when x is 3, y is 1, I get a slope of 2/3, so a little bit more shallow there. Okay, which makes sense because we're going down towards our horizontal slopes there. When x is 4, y is 1, I get a slope of 1/2, like so. Sorry, I should be sketching these slopes underneath there as well. Okay, when x is 3, y is 2, I get a slope of 4 over 3, 4/3, 1 and 1/3, so a little bigger than 1, a little bigger than 1. When x is 4, y is 2, I get a slope of, when x is 4, y is 2, I get a slope of 4 over 4, which is 1. Okay, when x is 2, y is 3, I skipped that one. I get a slope of 6 over 2, which is 3. Okay, so you can kind of see the shape that this is taking here. Let's see. Oops, sorry, that one I sketched the wrong way. I'm getting steeper as I'm going down. So I went and filled in the rest of those slopes in our slope field. This is looking a little bit crazy, huh? Kind of reminds me of one of those weird sweaters, I don't know, with all the hair sticking out of it. So now that we've got these, the last thing that we need to do is we need to sketch our solution curves based on those initial values that were given. My first initial value is y of 2 equals 1, which means when x is 2, y is 1. So that point is going to be right there. And if I follow my slopes, it's going to go up. But then, ooh, it's going to come down and uh-oh, I'm about to hit the undefined zone. So I need an open circle right there. All right, second solution curve will be red, and that contains the point when x is -1, y is -2, which is right there. Going to do the same thing. This seems like it's going down on the left, and on the right, it's going to be coming up and approaching again, up, undefined. Need an open circle there. And my last solution curve is passing through the point 3, -3, right here. So going down on the right and on the left, coming up, and wherever it intersects, it's going to be an open circle one more time. All right. So now that I've sketched my 3 possible solution curves, we can answer our question, which is, what happens to our solution curves as our x values approach 0 and y? And once again, we can say that all of our curves essentially stop, and we represent that with an open circle. When they reach the x-axis, okay, which is, or sorry, excuse me, when they reach the y-axis, which is when x equals 0. Okay, because we have undefined slope when x equals 0. Okay, and again, that's the key right there, that we have that undefined slope when x equals 0. All right, and this concludes our notes on section 7.2, slope direction fields.